All right, open up your book to section 1-5. This is on page 35 in your book. And the title of this section is Inverse Functions and Parametric Equations. The objective is, given a function, find its inverse relation and tell whether the inverse relation is a function. And secondly, graph parametric equations both by hand and on a grapher, and use parametric equations to graph the inverse of a function. So we're dealing with the inverse of a function. That's a topic that you've you've heard before, but we're going to make sure that we refresh our memory here on what an inverse actually is. And parametric equations are probably something new for you, but we'll go through how to sketch what a parametric equation. It turns out that those are really nice to use to try to graph an inverse, so we'll see how we can do that on our calculator. All right, a couple of terms to define here for us. An inverse is the relation formed by interchanging the variables of a function. That is, you swap the x's and y's. And usually when we swap the x's and y's, we then continue by taking that equation and solving it for y. Although technically you don't have to do that to have found the inverse. Once you swap the x's and y's, that's the equation that represents the inverse. Notice, by the way, that this says it's the relation formed by doing it. It doesn't say it's the function formed, it's the relation. Sometimes when you swap the x's and y's, you go from what started out as a function to something that's no longer a function. It just depends on what you start with. All right, so let's talk about how we find inverses. 3 different ways here. If you're trying to find an inverse algebraically, the inverse is found by swapping the x's and y's, and then you solve that for y. This is probably the way that you're used to finding an inverse. Swap your x's and y's and then solve for y. That's algebraically what we do to find an inverse. Graphically speaking, if I give you a sketch of a graph and ask you to sketch for me what the inverse looks like, it just means that you're actually finding a reflection. Graphically, the inverse is a reflection of the function across the line y equals x. So if you graph the line y equals x, that's just a linear function that goes to the origin that has a slope of 1. Graph that function. If you can sketch for me what the reflection across that line would look like, you've effectively sketched the inverse. And finally, numerically, what does it mean? Well, numerically, it means that the inverse is the set of ordered pairs y comma x. Notice, by the way, we've swapped those around. That's what we set up above there, is we're swapping x's and y's. So we swap them around as y comma x from the function. So if you're given a numerical representation for a function and you want to find points that are on your inverse, that's pretty straightforward. Just, again, swap your x's and your y's. All right. Next thing is the domain and range of our inverse. If you're working with a function, the domain of that function will become the range of the inverse. That should be intuitive as well, that if we're talking about swapping our x's and our y's, the x's are defined by the domain, the y's are defined by the range. If I swap those around, it should make sense that my domain becomes my range, and the second bullet there says my range of my function is going to be the domain of your inverse. So when you swap the x's and y's, you also swap the domain and range there. We use this term invertible. I pointed out on the previous slide that when we're talking about an inverse, that it's a relation we're talking about. That you might start out with a function, but when you swap your x's and y's to find the inverse, you might not end up with a function. We use this term here, invertible, to represent a function whose inverse is also a function. So if that relationship, when you end up swapping the x's and y's, turns out to be a function itself, then you are in fact invertible. Invertible just means that you start with a function and you end up with a function when you find the inverse. And if it turns out your function is invertible, so that means that you end up with a function when you find the inverse, then we call that an inverse function. And the inverse function is an inverse relation that is also a function. Thus your function's invertible. Those are interchangeable here. But if you end up with an inverse function, then we have a special notation that we use to indicate that it's an inverse function, and we write f, and we put a little superscript there of a -1 next to f, and then our independent variable x is in parentheses. So we do that to indicate there's a relationship that it has with the original function f, and that -1 indicates it's the inverse we're talking about. We do something similar when we're talking about reflecting points in geometry. We might take point A and reflect it across the line, and we call it A prime to indicate there's a relationship that it has with the original point A. That's all this is trying to do, is indicate there's a relationship to that original function f. Turns out that this is an inverse, and not only that, but it's a function that we end up with. The bad part about that notation, I guess, is that notation also is used to represent other things. And we'll talk about that in just a second here, but just realize that that special notation, f to the -1, that is something special. It means that you were talking about an inverse function. So that notation there that we're talking about for this inverse function, we read that as f inverse of x. When you read it, don't read it as raised to the -1. That sounds like it's a power function, or that you're raising something to a power. That's not what you're doing here. It's f inverse of x. If you read it the correct way, then you'll be less likely to do the wrong operation with it, or think that it means the wrong thing. All right, in fact, that's the last note here. When we talk about f inverse of x, we're not talking about the reciprocal. When you raise something else to a power of -1, that's what that means. But when we're talking about f inverse of x, that's not the same as 1 over f of x. That's not how you find the inverse function. We didn't start out by saying algebraically you take your function and flip it over and write it as 1 over f of x. We said you swap your x's and y's. That's the operation, is what f inverse of x means. All right, that's different than if you do this with a variable like, let's say, x to the -1. If I say x to the -1, x to the -1 does in fact mean that's the same as 1 over x. Or x to the -2, oops, to the -2, is the same as 1 over x squared. That's what the power definition tells me. All right, that's what my laws of exponents tell me. This is not referring to that when I talk about this f inverse of x. We're not reciprocating something. We've actually swapped x's and y's, and then we solve that for y. All right, so let's take a look at a couple of examples here. Start with example 1 on page 38. For this example here, they've given us a function, f of x is equal to 0.5 x squared plus 2. So they've given us a quadratic function here, it looks like. Let's go ahead and write that down. F of x is equal to 0.5 x squared plus 2. And it says they want us to make a table of values for f of -2, -1, 0, 1, and 2. And from the numbers in the table, explain why you cannot find a unique value of x if f of x is equal to 2.5. And how does this result tell you the function is not invertible? Okay, so let's plug in these different values into this function and see what we end up with. Let's just go ahead and make a table of values here. So I'll say x and f of x here. Try to give ourselves enough room here to fit all this in. They want us to go from -2 all the way up to 2 here. So -2, -1, 0, 1, and 2. Okay. So when we plug in -2 into this function, -2 squared is going to be a +4, times 0.5 is 2, plus 2 is going to give us a value of 4. So at x equals -2, we should be getting a value of 4. When we plug in -1, -1 squared is 1 times a half is 1/2 plus 2 would give us 2.5. Plugging in 0, 0 squared is 0 times a half is still 0 plus 2 is going to give us 2. When we plug in 1, 1 squared times a half, well, actually we just did that, but because when we took the -1 and squared it, we got a +1. So this turns out to be 2.5. And when we plug in +2, we're going to get the same result that we get for -2. Okay, so there's a table of values there. That's the first thing. From the numbers in the table, explain why you cannot find a unique value of x if f of x is equal to 2.5. Well, I guess we see that in our table here, right? I can see that there's 2 places where I got a value of 2.5. So that means that when x is equal to -1 and when x is equal to 1, I get the same result, the same output, 2.5. And the last question they asked you there is, how does this result tell you that the function is not invertible? Well, in order for it to be invertible, that means that for any one input into the inverse, I have to have one output. Well, I can see that when I swap my x's and y's here, and I have an input of 2.5, that I'll have 2 different outputs. I'll have an output of a -1 and an output of 1. So because of that fact, I can tell that this thing's not going to be invertible. All right. Part B says to plot the 5 points in part A on graph paper. So we'll do that. I got a piece of graph paper here. You might do the same thing on graph paper, or just kind of draw yourself a sketch there to give yourself a decent window to work with. So -2 to 4 is our first point there. So if I plot that first point at -2, -2, and then go up to 1, 2, 4. That'll be right there. So this is at 4. This is at -2. And then -1 is at 2.5. So -1 is up at 2.5. So that's going to be right here. And at 0, we had a value of 2. 0, 2. And 1 and 2.5. And the last one was at 2. We're back up at 4. And it said to connect these with a nice smooth curve here, so I'll draw a little line that goes through here. Something like that. All right, to plot the 5 points, connect the points with a smooth curve. And then on the same axes, plot the 5 points for the inverse relation and connect them with another smooth curve. So now that I've got a table of values, again, just swapping the x's and y's is real easy to do. So instead of plotting the first point at x equals -2, y is equal to 4, I'm going to instead plot that at the point x is 4, y is -2. So if I go out to 4 and -2, this is 4 and -2, I'll plot a point there. And then the next point is at, instead of -1, 2.5, I'm going to go to 2.5 and down -1. That'll be about right here. And the next point, instead of being at x equals 0, y equals 2, it's x equals 2, y equals 0. So that's right there. And keep going there. So then I'll plot the point at x equals 2.5, y equals a +1, and then finally at 4, +2. And we'll connect those with a nice smooth curve that goes through those. All right. And then it says, how does the graph of the inverse relation confirm it is a function? Well, if you sketch, like we said, graphically, if you sketch the line y equals x along with this, y equals x would be this line that goes right through here. That looks like if I do a reflection across that line, take the green original function, reflect it across the line y equals x, I'll end up with the inverse there. But the inverse is definitely not a function. It does not pass the vertical line test. So the inverse is not a function. That is, this function is not invertible. All right, and then for part C, it says now find an equation for the inverse relation, plot f and its inverse on the same screen on your grapher, and show that the graphs are reflections over the line y equals x. So I guess we're going to verify what we just came up with here. But now for part C on this thing. we have, I'm going to write it in terms of x and y. So we have y is equal to 0.5x squared plus 2 was our original function there. And now the first step is to swap your x's and y's. So algebraically, we'd end up with x is equal to 0.5y squared plus 2. That's the swapping that takes place there. And now we try to solve this for y. So let's subtract 2. So we have x minus 2 is equal to 0.5y squared. Get rid of the 0.5 by dividing by 0.5 or multiplying by 2, however you want to say that. I'll write it as 2x minus 4 when I multiply by 2 is equal to y squared. And then finally get rid of the y squared by taking the square root of both sides. Don't forget when you do that, you get two solutions here, a plus or a minus. We have plus or minus the square root of 2x minus 4 is equal to y. There is what y equals. And now you can see why this is not a function. If I plug in one value of x, this says to calculate this square root and write down both the positive and the negative answer from that, plus or minus. All right, so let's grab our calculator and sketch this. They wanted us to do that. All right, so on our calculator, go to your y equals menu. Let's go ahead and put in the original function here. It's 0.5x squared plus 2. And then I'm going to put this equation in here 2 times, or that's the way I'm going to do it, at least to start off with here. That the inverse was the square root of 2x minus 4. And then it was also the opposite of that, square root, the opposite of the square root of 2x minus 4. And I'm going to change my window here. I'm going to do this in a square window so that it does not look distorted here. So the standard window here isn't going to quite work. Let's go to our zoom menu and go down to zoom square. Oops, number 5. That'll give me a square window, and hopefully it'll look like it's at least proportional here. I got more x values showing than y values, so that's why it does look a little bit different, but at least there's some proportion to this. And in fact, if you sketch the line y equals x along with it, you should be able to see that there's a reflection here. If I take and reflect the blue graph across the line y equals x, it looks like I would end up with that red and black graph right that's laying right on top of. Let's in fact grab ourselves a little picture of that. We'll paste it in there. All right, there we go. That was part C on that example. Now in the objective here, it mentions something about parametric equations. So what exactly is a parametric equation? A parametric equation is actually 2 equations that define one graph here. 2 equations in which both the x and the y are expressed as a function of a third variable, t. So instead of having just one independent variable and one dependent variable, instead, when we're dealing with parametric equations, you still only have one independent variable, that's t. But when we go to graph this, we'll find that there's no t-axis here, so there's nothing that shows up in terms of our points we're plotting when we plot something with t. And instead, x and y are defined in terms of t. So you'll plug this value of t into the equation for x, do the same for y, and that will give us a point to plot. So that's what a parametric equation is. It introduces a new independent variable, and x becomes a dependent variable along with y. All right, so take a look at example 2, just to get some practice here of what a parametric equation looks like. They give us an example here to work with. It says on graph paper, plot the graph of these parametric equations by first calculating values of x and y for integer values from -3 through 7. All right, so let's write down our parametric equations that they've given us here. They're telling us that x, I'm going to write it as x of t. You can call it x of 1 if you want to, but we only have one parametric equation here, so x of t is equal to the absolute value of t minus 2. And y of t is equal to the square root of t plus 2. So to come up with our set of values that we're going to, or our t table here of values, we'll create a list of x, y, and t values that we're going to go through and plot. And I'll plug in a few of these values, and then we'll just take the numbers that they give us from the book to sketch this thing. But what we're going to do is we're going to take this value of t, they said to start at t equals -3, and plug it into the x equation, plug it into the y equation, that becomes a point for us that we're going to plot. So when I plug in -3 into x, -3 minus 2 is a -5. The absolute value of that is a +5. That's the x value. Do the same for the y value. So -3 plus 2, well, that's going to be a problem, right? That's going to be the square root of a negative number. So this does not exist here. So there's no point to plot for t equals 3. Now move on to the next t value. If you go to t equals -2, when I plug in t equals -2, -2 minus 2 is a -4. The absolute value of that is a +4 for x. -2 plus 2 is 0, so the square root of that is 0. So for the y value, we get 0. And we continue doing this. We'll do this for a couple more points here, and then we'll plot the data that they gave us. So when I plug in a -1 into x, -1 minus 2 is a -3. The absolute value of that is a +3. Plug in -1 into y. I have a -1 plus 2. That's a +1. Square root of 1 is 1. And let's plug in the 0 here. When I plug in the 0, 0 minus 2, that's a -2. The absolute value of that is +2. 0 plus 2, that's going to be 2. Square root of 2 is what, 1.414. Grab your calculator and check that out, but that's what I think we should get, and so forth. All right, we continue doing this. Notice that you're taking a value for t. You're just picking numbers to plug in. You plug that into each equation, and that tells you an ordered pair that you're going to plot. So let's try plotting these values just so we can see what this graph would look like if we plotted all these points from -3 to 7, I think they said to do. So I'm going to take the table of data that they've given us there in the book. And again, as I plot this, notice that I'm not plotting anything for the t value. So even though I had t's listed in my table up above, there's nothing I'm plotting down below here. It's just simply x and y values. So the first point that I have was at x equals 5, and there was no y value there. So we are going to skip plotting that point. The next point was at 4, 0. I guess based on the data that I have here, let me change my scale a little bit here. Let's make this, yeah, I think I can do this. 1, 2, 3, 4. And the y values, we'll do 1, 2, 3, 4. Yeah, I think we should be able to fit that on there. Oops, it does go out to, oh no, I don't have to go out to 5 there. All right, so let's plot these points here. So the first point there at x is 4, y is 0, so that's going to be this point right here. The second point that we got was x was 3, y was 1, so x equals 3, y equals 1. And then the next point at x equals 2, we got the square root of 2, which is 1.414, so that's about right here, we'll say. And the next value is at x is 1, and then that's the square root of 3, so that's going to be 1 square root of 3 is 1.7 something, is about right here. And then at x equals 0, we got a y value of 2 is what we would have got. We didn't plug those ones in, but we would have gotten those values if we would have kept going in our table. When x is 1, we get a value of 2.23, so that's about right here. When x is 2, we get 2.4, so that's going to be about right here. And when x is 3, we get 2.6, so it's just above here. And when x is 4, we get 2.8. And finally, when x is 5, we get 3. I didn't mark this 5 out here. I'll put that on here. So this is at 5. Okay, so now we can sketch a nice little curve that goes through these points. And we should end up with something that looks like this has a little bit of a curve to it. These almost look like they might be straight. I don't know if they're supposed to be or not, but there we go. There's what our sketch would end up looking like. Okay. Notice that we don't end up with a function. This is a parametric equation, and this is how we actually plot the points that make up our parametric equation. And actually, that's what your calculator or any software would use to come up with these sketches for us. All right. I think that's all they asked us to do with this example, was just to make a table of values and then plot those points. Okay. All right, let's take a look at one last example here, and we're going to do this a couple of ways, although they only asked us to do it one way in the book. But it says to plot the graph of y equals 0.5 x squared. Oops. Y equals 0.5 x squared plus 2. And it says for x in the domain from -2 to 4, so we're talking about a restricted domain. And it says use a convenient t-step of 0.1. We'll see what that means there when we go to graph this. And the graph will be similar to, or sorry, I'm reading the wrong part here. Let me read that again. Plot the graphs of the graph of y equals 0.5 x squared plus 2 for x in the domain from -2 to 4, and its inverse using parametric equations. And what do you observe about the domain and range of the function and its inverse? Well, we've kind of already stated that what the relationship between the domain and the range should be. But let's see what we end up with. All right, so let's do this a couple of ways. One way it says to do this is with parametric equations. I'll call that A here. So if I want to plug this into my calculator using parametric equations, I've got to split this up into two equations. The easiest way to do that is, and by the way, there's several ways you could do this, but the easiest way to do this is just to name x as your parameter t. So we're going to define x equal to t. And then you can say that y is equal to 0.5 instead of x squared. Since x is equal to t, it'll be t squared plus 2. Again, you've got several ways you could actually do this, a number of ways you could actually do this. This is the easiest. Just simply say x is your t and then rewrite y in terms of t. And there you go. You've got yourself a parametric equation. This will graph for us the original function. If I want to sketch the inverse, this is the nice thing about using parametrics to do this, is that algebraically all I have to do is swap x's and y's. And notice that I've already got this defined in terms of x and y. So if I literally swap those around, I can get the inverse. This is the original. So for the inverse, I can swap these around. Instead of x being t, I'll say x is equal to the 0.5 t squared plus 2. And the y is going to be equal to the t. Again, notice that all we've done here is I've taken and swapped these two, swapped the x's and y's in order to get my inverse. So it's really easy to sketch the inverse in parametric mode on your calculator. Okay, so let's try that out. And then we're going to try the other method here, this draw inverse command, just to show you what that looks like. So grab your calculator. And the first thing that you got to do, first thing that you got to do is go to your mode, and we're going to switch from being in function mode to parametric mode. So under mode and find parametric mode. And then when you go to your y equals menu, I got some functions in there that I'll get rid of. You'll notice that in your y equals menu, it looks a little bit different because now I have an equation for x that I have to write as well as an equation for y that I have to write. So I've got to write both of these. So let's go ahead and do that. Let's first graph the original equation here. So we're going to graph x equals t, and then y was equal to 0.5 t squared plus 2. And I'm going to go ahead and punch in what the inverse is going to be. Again, all I got to do is take these two equations and swap them around. So the x is the 0.5 t squared plus 2. By the way, notice that your xt theta n button up there changes to t for you automatically because I'm in parametric mode if you didn't realize that. And then finally, your y is equal to t for the inverse there. When you go to your window, you'll notice your window's got some different options here now as well. Now in my window, I can change what range I want my t values to go. So they said to go from -3 to, or sorry, they said to go from -2 to 4 for this one for our x's. And since I'm saying that x is equal to t, I'm going to do the same thing here. So I'm going to go from -2 to 4. And they say use a, or I'm going to use a t-step there of 0.1. And I think I'll just do this in the standard window here. You could zoom in perhaps a little bit if you wanted to. All right, and we should be able to graph this and see what our functions look like. I guess, I don't know if it went off the screen there. Maybe I should go a little bit further in my positive direction here. Let's go up to 12 in both my x and y direction there. Just make sure, there we go. So they're both on the screen there, okay? If you want to put this in a square window, that way they look proportional, that's fine. But you should see that if you graph the line y equals x along with this in a square window, that the blue graph would be reflected over onto the red graph there. In fact, let's grab a picture of that. We can paste it in here. Just drop them in right there. All right. Now the other way that you can do this is you actually have a command on your calculator called draw inv for inverse. So if we go back to our calculator, I'm going to get out of function or out of parametric mode here to do this and go back to function mode. In fact, I'm going to go back to just the original equation here, 0.5 x squared plus 2. I'm going to go ahead and put that in y1 so you can see what that looks like. Again, if you want to get a square window in there, that's fine too, but I'm just going to do this in this window here. And under your draw menu, if you go to second draw, second and then your program button, you'll find that you have this command down here called draw inv, draw inverse. Now since I already defined the function in y1, I can just tell it to draw the inverse of y1. That's what I'm going to do. So draw inverse and then go to your variables, go over to y variables, grab function y1, and then just press enter, and it will sketch along with your graph now the inverse of that. That's another way that you can quickly get a sketch of the inverse, right? One way to do it with parametrics, one way to do it with the draw inverse command. All right, and that's the first half of this section.